All right, everybody. Let's talk about nuclear chemistry some more. So this is a review slide of what we covered the other day. That has all the different types of radioactive decay. Again, this gamma is not really nuclear decay. Because it's really just the radiation, the light that comes away from all these other reactions. So let's talk about a couple other concepts. One of the things that winds up being important when we start dealing with radiation is how do we protect ourselves from radiation? How do we prevent any tissue damage? And this is really what they kind of were missing in the early days. They didn't understand a lot of this, partly because biochemistry didn't exist as a field of study until about the 1950s or so. Up until then, there really was not a whole lot of understanding of cellular processes and how reactions happened in the cells, and let alone understanding what DNA was or its role in cellular division. So it's kind of understandable that they didn't understand what they were doing when it came to protecting themselves from radiation. In general, when we're talking about radiation, alpha particles tend to be, they're the heaviest types of radiation, because remember, if we were talking about alpha particles, that's really a helium nucleus, right? About a mass of 4, but then we also had beta particles, which were basically an electron that had a mass of 0, right? And then there were some other types of fission that can happen, but then then there was the positrons, which was just a positively charged electron. Both of these are the same size, right? They're both charged. They can both cause damage, but really it's the alpha particles that are the heaviest. If you think of the electrons being like a bullet going into your cells to break stuff up, this is like a cannonball. If they have the same amount of energy, though, these are definitely going to go further, right? They're going to move further into the material before they hit something where they kind of lodge into place and cause damage. So we refer to that as penetrating ability or penetrating power. These beta particles and positrons have a lot more penetrating power, but they're also a lot less dangerous. So alpha particles are really dangerous, but they can be stopped by a piece of lead that's 1/100th of a millimeter thick. Right, so that's like thinner than a sheet of paper. And really, even if it's not lead, generally we can block radiation. The more dense something is, the better it is at blocking radiation, just because there's more stuff in the way. The beta particles, on the other hand, they'll go straight through that first piece of lead, but if they hit a piece of lead that's 1 millimeter thick, that's enough to stop beta particles generally. It's enough to stop most of them on average. But that gamma radiation, though, is super high energy, and it actually will go right through just about anything. Get high energy light. Basically, in order to stop that light, you need something that has an electronic transition that's relatively close to that same energy in order for that light to get absorbed. And so any sort of radiation that comes from a nuclear process will move right through most of, so 100 millimeters. How big is that? 10 centimeters, right? So about there. So you would need a piece of lead that thick is not even enough to stop gamma radiation or X-rays. So then what's the whole point of the the little lead vest you have to wear at the dentist's office.
It absorbs that alpha beta particle.
Except that they're not using alpha and beta particles to take x-rays, right?
Comfort.
Basically comfort. It might have a little bit of protective power, but really the best thing to do is to leave the room, which is what the nurses and the dentists do, right? And that actually makes sense. The amount of radiation that they use for x-rays is pretty insignificant if you're talking about getting an x-ray once a year, once every 2 years or something like that. It's a pretty tiny amount of radiation. It's not likely to actually cause any issues. I think you actually get more radiation exposure from eating a banana once a week than you do from getting an x-ray once a year. Yeah. They produce positrons. They decay. There's a form of the potassium. Bananas are high in potassium, right? And potassium on Earth has a certain ratio of, is it potassium 20? That makes sense? Yeah, probably potassium 20. That decays by emitting positrons. And when it does so, it also produces radiation along with it. So, and they actually, you can rank, there's a lot of weird units that when it comes to radiation. There's radioactivity, which is how many decay events happen per second. And then there's also things like absorbed radiation dose or effective radiation dose that has to do with what type of tissue got exposed to radiation and what type of radiation was it, in addition to just how much radiation. So the health effects of radiation are a lot trickier to quantify than just how much radiation occurs. But in general, I think you actually get more radiation exposure also if you go on an airplane. You go on a commercial airplane flight, you go high enough up into the atmosphere that the Earth's magnetic field is not protecting you as much, and the Earth's atmosphere is not absorbing as much of that high energy radiation. So you actually get more radiation exposure from just going on an airplane than you do from getting an X-ray. Oddly enough, you don't see anybody like worried about going on airplanes when it comes to radiation exposure, right? It's always getting X-rays or radioactive waste. But potassium 40, not potassium 20, potassium 40. That makes more sense.
Give it get less radiation if you're flying at night than, or you're still just
I believe
in the upper atmosphere.
I believe so, but there is background radiation in the upper atmosphere because light gets scattered around the upper atmosphere, and the higher energy the light, the more it gets scattered by gas particles. So you should be less, but it'll still be a significant amount, measurable amount. All right, so let's do a practice. Potassium 40. It decays. It can either emit a beta particle or it can go through electron capture, depending on the conditions and probability. What would that reaction look like? If potassium 40 if it goes through an electron capture, then it's basically grabbing a beta particle, right? That has a -1 charge and a mass of 0. What is it going to turn into? So that's going to take one of those protons and turn it into a neutron. So we just are going to get argon. Still going to weigh a mass of 40. We just have 18 protons instead. Basically, you took that extra electron and you stuck it onto a proton and canceled out the charge. Right? And so if you add up these protons, these charges here, that gives us our product. And everything's balanced. We have the same number of charges on the left-hand side and the same mass on both sides. So that's if it went through electron capture. The other process is it can emit a beta particle. So still potassium 40. If it emits a beta particle, then we're giving off the electron instead of absorbing the electron. So now it's still going to be something with a mass of 40, except now we took one of those neutrons and turned it into a proton. So we get 20, which is calcium. Turns out both of these are really, really slow processes, slow enough to the point that you can use it to verify our uranium lead dating scheme. So we're talking about it's going to decay on the order of 1 billion years for its half-life. So it's not decaying quickly, but it does decay. So how do we decide which of these is going to be more stable? What type of, it's one thing for me to tell you what type of decay something goes through. How do you predict that ahead of time? Well, it turns out if you understand strong and weak nuclear force, we can actually run the numbers. It turns out the most important things in terms of strong and weak nuclear force are neutrons, in the ratio of neutrons to protons. It turns out that there's sort of a sweet spot that they call the valley of stability. And the valley of stability is basically where you have the right ratio of protons to neutrons, you get a stable nucleus. So all of the blue-green dots are stable nuclei. Nuclei that are stable enough that they don't go through any sort of radioactive decay on any sort of measurable timeline. So they're not all equally stable, but they're all so stable that the nucleus is not going to fall apart. And all the yellow spots are isotopes that are either occur naturally or we're able to make with particle accelerators. They're stable enough we can make them, but they're all radioactive. And basically all the white area then is stuff that's so unstable we can't even make it with a particle accelerator. Technically, you can have any ratio of protons and neutrons you want. Technically, you could have potassium 72 instead of potassium 40 with a ton more neutrons in it. But having that many neutrons, what that would look like on this graph, so how many neutrons would that be for potassium then? 19 protons, 72 minus 19 is what? It's going to be 51? 53? So if we follow that right here, 19 is our number of nuclei. If we went all the way up to 50 something, 53, we're way up in this section right here, right? That's so unstable that it won't stick together. We can try to make that with a particle accelerator, but it'll just fall apart faster than we can measure it. So only in this valley of stability do we actually see isotopes stable enough to either exist indefinitely or last long enough for us to measure them at least. And it has to do with that ratio of protons to neutrons. So this ratio here that they have written here, this red line represents 1 neutron for every 1 proton. So that's a 1-to-1 ratio. And so you can see that we really see things that are most stable when you've got a few extra neutrons relative to the number of protons. Turns out the most stable ratio is like 1.6 once you start getting into the heavier atoms. And basically, at the lighter atoms, 1-to-1 is pretty stable. As you get larger and larger nuclei, you need more neutrons to basically keep it stable. And you'll notice once you get past a certain number of protons, there are no more green dots. Right? Once you get past mass of 82, everything is radioactive. Basically, it doesn't matter how many neutrons once you get to that point, that those nuclei are so unstable they will always fall apart given enough time. And so lead is our highest stable number of protons. Everything past lead is radioactive, at least a little bit. It might be really, really slow the way that it breaks down, but everything past lead breaks down. And you can kind of see that those green dots, has a little bit of a curve to it. You start needing more and more neutrons, the heavier the atoms get. And if you look at something like uranium, uranium's more stable nuclei is 238 to 92 protons. So 238 minus 92 is 144. No, 146. So 146 over 92 is going to be something like more than a 1.5 ratio. So pretty close to 1.5, but right. So if we know that getting to this valley of stability is where we get stable isotopes, we can kind of think of these reactions as being, they're always just trying to get closer to one of those stable isotopes. So if you have too many neutrons, if you're on the upper left quadrant here, that means you've got too many neutrons relative to your number of protons. If you have too many neutrons, what type of decay is going to be more likely? So if we have too many neutrons, we want to take a neutron and turn it into a proton. Beta decay. Right? So for instance, if we had so zirconium 9040, we had zirconium 9240. That's too many extra neutrons, right? So if we turn one of those neutrons into a proton by going through beta decay, now all of a sudden we still have a mass of 92, but now it's 41. That's not zirconium, it's niobium. And now all of a sudden that took us closer to that right ratio that we want to see, right? We were at 1.5, above 1.5. Now we're a little bit closer to 1.5. That moves us closer to that valley of stability. If we look at 41 here, it looks like about 62 or 63 neutrons is where you get stable. We're still not quite there. We still have a few more neutrons than we would like. So it might go through another radioactive decay. What if the opposite's true? What if we're in this bottom right corner? If we have too many protons and not enough neutrons. So that's kind of a tricky one, but we can look at this one. Electron capture or positron emission. Basically, we want to do the opposite here. We can either capture an electron or turn a neutron into a proton, or sorry, turn a proton into a neutron, or we can give off a positron. If we do that, we're going to get what? Hydrogen 3. And so I'm not going to ask you to do these sort of predictions on the test. It's just a concept. I don't want you to think it's random what type of decay these things go through. There is reason to it. It has to do with balancing out the right number of neutrons to protons. And then once you get past lead, once you get past 82, almost everything will go through either fission, where it just straight up splits apart into pieces, or it'll go through alpha decay. Because alpha decay basically is just a way to just lop off a chunk of the nucleus and get it smaller. So the whole point of alpha decay is that it gets all of our nuclei that are up in that top right corner down into the left. Right, so if you're losing 2 protons and 2 neutrons, you're moving in a straight line down into the left on this graph. Right, and that's why we get things like these decay series. So uranium-238, we use that as an example a lot. It's just straight up too big. It's not just that it doesn't have the right ratio of neutrons to protons. There is no stable ratio of neutrons to protons when it comes to uranium. So what does it do? It basically starts dropping protons and neutrons. So uranium-238 will turn into thorium-234, which then goes through a couple of beta decays and then through a whole bunch of alpha decays. So they just straight up make it smaller. And that gets us closer to that valley of stability. So we'll go back to looking at this graph again. If there are no stable isotopes once we get past lead, what's the whole point of trying to fill in the periodic table past that? Trying to make these isotopes, these new elements, like, you know, number 118, Ogain-san. I have no idea how to actually pronounce that because I don't know how to pronounce the guy's name in the first place. But I know it's spelled Ogain-san. Why do we bother trying to make these things if we know they're going to be radioactive, and almost everything has really short half-lives once we get up to that high? Well, it's really cool, and we don't necessarily know what we're going to find until we find it. But we can look at those strong and weak nuclear force. So this is a different view of that same valley of stability. Except instead of valley of stability, we made it so it looks like islands instead. Instead of being a valley. So all of these stable isotopes are that maroon color. And the shorter their half-life, the faster they decay, the shorter they are here. So the blue is less stable. There's this little island out here that shows that there should be some really stable elements that are bigger than what we expect, potentially, if we can find a way to make those elements. But then again, not everything necessarily follows exactly what we expect. So we're basically trying to find this island of stability out there by using particle accelerators to smash stuff together to try and make new elements, with the thought that one of these new elements we make might have a stable isotope. That stable isotope might have really interesting properties. It might be a really good conductor. It might be really useful for mediating fusion reactions. There's a lot of possibilities as to what properties those materials will have, but we don't know until we make them. So we're basically just kind of taking the scattershot approach, trying to make them as any way we can to try and find that island of stability. All right. Now I promised that we'd get a chance to look at calculations, because everybody wants to do calculations with this, right? It's about what I expected. All right, so we talked about this. Basically, we're just going to do some practice problems and define some more vocabulary when it comes to that E equals MC squared. Right, so we already mentioned that there was sort of a difference between the mass of a nucleus and adding together all of its pieces. So if we look at something like If we say, okay, the mass of a proton is 1.0078 AMU, grams per mole, and the mass of a neutron is 1.00, I think it's just the same numbers flipped, 87 AMU. Then if we have a nucleus that's made up like, what's something that only has one stable isotope? Let's look at fluorine. Fluorine only has one stable isotope. It's got a mass of 18.998. How come it's not the same as 9 of these and 10 of these? Without even doing the math, we know that that's not going to add up to the right amount, right? There's some mass that's missing, right? And so we call that mass defect. Mass defect is the difference in mass between adding up all the pieces individually and what the nucleus actually weighs. Right? It turns out that that's, even if we're not talking about a nuclear reaction happening, that difference in mass is going towards holding the nucleus together, right? Which we call the nuclear binding energy. So in this case, what is the nuclear binding energy? How can we figure that out? Well, if we know that E equals mc squared, whatever our mass defect is, we're going to plug in for mass. But it's got to be in kilograms in order to make this work. Because as somebody asked the other day, what are the units on these? Well, if we want our energy to come out in energy units, come out in joules, we need our mass to be in kilograms, and we need speed of light to be in meters per second. So this is an AMU, which is also the same as grams per mole, right? So we could convert that into kilograms per mole, couldn't we? Just do a quick divide by 1,000. Although we might as well get our mass defect before we worry about switching the units. What do we get when we take 9 of these and 10 of these and put them together? More than 19, but if we're actually going to do the math here, let's actually get a number for it. $1,572. So our mass defect then is we just do the subtraction. So it's going to be 0. What do we get? I can't borrow in my head. 1.5. Let's call it 159 since we only go out to the thousandths place here. Seems like a pretty small amount, measurable amount, but a pretty small number, right? Especially once we put it into kilograms per mole. So that's going to be 1.59 times 10 to the minus 4 kilograms per mole. We just divide this by 1,000. Get 1.59 10 to the minus 4 kilograms per mole. So if we plug that in though, 1.59 10 to the minus 4 kilograms per mole. What's the speed of light? Anybody have that one memorized? .998 times 10 to the 8 meters per second. We're going to square that. Now it's looking like a fairly large number, right? This is going to be really close to 9 times 10 to the 16. back within sig figs, we can just call it 9 times 10 to the 16. Got to square our units too. That's what's going to make our joules work out here. What do we get? And now that's kilograms times meters squared over seconds squared. So that's just joules per mole. Okay, but joules 10 to the 13 seems like it's a big number, but we need context, right? So since we usually do reactions in terms of kilojoules per mole, we could divide by 1,000, put it in kilojoules per mole. 10 to the 10 kilojoules per mole. So to put that number into context, combustion of gasoline is something like 2,000 kilojoules per mole. This is 10 to the 10, right? It's 10 to the 6 is 1,000,000 kilojoules per mole. This is something like 14 billion kilojoules per mole. The combustion of gasoline is about 2,000 kilojoules per mole. Like, we're wildly different scales when it comes to the amount of energy. There's a reason why nuclear weapons and nuclear power plants are on a whole different scale compared to any sort of combustion or any other standard chemical reaction. It's not even close. Right? So to put it in terms, it's a little bit dumb, but the easiest way to visualize this is to think about it like an explosion. Right? That first nuclear bomb that was dropped on Hiroshima was about 10 kilotons of TNT. So that was one bomb that was roughly the size of this podium. When it detonated, it gave off the equivalent energy to 10,000 tons of TNT. Right? 10,000 tons of TNT. I don't even have a good way to visualize it, but it's going to be pretty close to if we filled this entire building with TNT. Right? For context, all of the airstrikes on Germany, on Dresden during World War II, over the course of the entire war, was roughly equivalent to that first bomb. Like, it's not even comparable, which is why when you have things like the Geneva Convention, nuclear weapons are not categorized like other bombs because it's just totally its own thing. Right? It's not even close to the same. All right, so how do we do the similar calculations for a nuclear reaction? We do it the same way. We just look at what's the mass of all the pieces that we end up with. We do final minus initial to get our delta M. In this case, we were talking about an individual isotope. How much energy does it take to hold that nucleus together? The nucleus of a fluorine atom takes this much energy to hold it together. But it's the same reaction, or it's the same calculation that we do for any nuclear reaction. You look at the pieces and you do final minus initial. In this case, it's just here's our initial and here's our final. Alright, and so we can actually look at all the stable nuclei. The most stable nucleus of every element. As we go from hydrogen all the way up to uranium. There's actually like a theoretical maximum where you get the most nuclear binding energy. And we think of those as being the most stable nuclei. The most stable isotopes are the ones where you have the highest possible nuclear binding energy. And that happens between iron 56 and I think it's not lead. Maybe something around 75. I don't actually know. It's probably tungsten. Yeah.
They're using the slide in.
Mega electron volts. So if we do this, you notice we did this in kilograms per mole. If we just leave it in AMU and convert AMU to kilograms, we get the amount of binding energy for a single nucleus instead of for a mole of nuclei. And if you do that, when you get meters squared over second squared times kilograms, you'll get joules for a single nucleus instead of joules per mole of nucleus. But that's not really all that useful because it winds up being a really, really tiny number. So they convert it into what the physicists call atomic energy units, which is just electron volts. So that's the energy of a single nucleus instead of a mole of nuclei. In chemistry, because we're used to thinking about per mole, and kilojoules per mole is already a comfortable unit for us, it makes more sense to do it this way. And then we don't need to worry about memorizing that conversion for AMU to kilograms also. And so in general, everything in the universe, every nucleus in the universe is on its way towards this yellow region. Once you get something into this yellow region, it basically will stay in that yellow region, unless there's something like a supernova. In which case it'll temporarily get bumped outside and then go through radioactive decay to get back to that yellow region. So this is similar to our valley of stability. On a long enough timeline, every nucleus in the universe will eventually be something in that yellow region. Right? Because those are the most stable nuclei. Everything smaller than that can go through fusion to become more stable. Everything larger than that can go through fission to become more stable. Which is kind of a weird thing to think about because humans like to see our particular environment as being like more important or like the ideal because it's what we're used to, what we're evolved to. But it's the particular ratio of elements and isotopes in the biosphere on Earth are all just kind of because that's the solar system that life evolved in. Right? In a different solar system, if life evolved, it'd have a different ratio of these different elements. And that ratio might be governed by how large was the star that went supernova there. Our supernova star that went supernova before our sun happened to give us a very specific ratio of all these elements that gives us all of our atomic masses and all of our isotopic ratios. Other solar systems, that's all going to be different. Which is kind of wild to think about. All right, so how do we do this with the nuclear reactions instead of just looking at the individual pieces? We do the exact same thing. You add up the pieces and do final minus initial. So here's our uranium reaction. They've already done the addition for us. So this is the nuclear reaction that yields that was the detonation in that Hiroshima bomb was basically uranium-235, which when it breaks apart, it gives off 3 neutrons. If one of those 3 neutrons happens to get lodged inside the nucleus of another uranium-235, it does that process again. And every time that process happens, you generate 3 more neutrons. So you can see that as this reaction progresses, we're going to wind up with it sort of, it's called a runaway reaction, where it's just going to pick up speed as it goes. The more times this reaction happens, the more neutrons you have flying around, the more neutrons you have flying around, the more this reaction happens. They also call that autocatalytic, in that the products of the reaction catalyze the reaction happening again. So basically, what if you have a large enough chunk of uranium-235, this runaway reaction winds up happening so fast that effectively all of your uranium goes through this fission process. Anybody know what they call that? There's a certain threshold where once you get more uranium than that, it causes it to detonate. Anybody have an idea what that might be called? You need a certain level, certain threshold. If you get past that, something happens. It's a common term. I guarantee you've all heard it before. It's called critical mass. Critical mass is the cutoff where you have enough uranium that more of these neutrons are being captured and causing more fission than are escaping to the surroundings. Once you get past that cutoff, you get a nuclear explosion. So this is the part where I get to teach you how to build a nuclear bomb. All you need is a critical mass worth of uranium-235. Easy enough to come by. Now that we have Five Below in town, right? We can go down to Five Below, pick up our uranium. But basically all this they did was they had a big chunk of uranium-235 that was about 0.7 times the critical mass. They measured it. There was they did a whole in the Los Alamos projects. That's one of the things they had to measure is what happened when they started putting larger and larger amounts of uranium together to try and estimate what critical mass was.
Yes.
I think it was a chunk about this big was 1/2 of the reaction.
Don't get a basketball.
Don't get a basketball worth of uranium. Basically, all they did was they put this in a tube, and they put a whole bunch of TNT behind it. And then they had on the other end of the tube, they had another chunk of uranium. With a whole bunch of TNT behind it.
I can see this.
Literally just fired 2 giant uranium cannonballs at each other, hard enough that they fused together. And when you put both of these together, you were well over critical mass. Yeah. No. No, my wife has a family friend who's actually a uranium salesman, which is a weird business to find yourself in. But he literally, his job is to wine and dine like government officials and heads of state. He travels around the world to power companies and governments and sells them uranium, not uranium-235, uranium-238, because that's what you use for power plants. Uranium-235 is what you use for nuclear bombs. Well, they have like they have about that much in each of them. It's just basically the way smoke detectors work is you take a small radioactive sample and you put that small radioactive sample over here. It's going to give off alpha particles. And then you have a detector over here, a Geiger counter. I think I mixed up the I and the E there. And so basically what your smoke detector is doing is it's constantly detecting alpha particles from that small radioactive sample. And if smoke gets in the way, it basically just blocks those alpha particles from hitting the Geiger counter. And so what a Geiger counter and when that Geiger counter is not detecting a sample, it actually just completes a circuit, which causes it to start beeping. So that's why smoke detectors, it's not just smoke that sets them off, right? Has anybody ever had a smoke detector right outside a bathroom? You take a hot, steamy shower, that's enough to set off a smoke detector sometimes. Zach? Let me see if I don't have that one on here.
There's a great video on that.
There's a good video on that. There's also.
There's the one where
You measure the radiation and you have to eat in an hour.
Right. That was back in like 19. So it's just like found it's like in one of their systems. Yeah.
That's 235.
That would have been a natural mixture of 235 and 230. All right. So I really like this figure for describing how radiation works. Basically, this is a logarithmic scale. So all the stuff on the left-hand side. Oh, that's
next to someone breathe.
people give off radiation, it turns out. Everybody's radioactive. Everybody has potassium in them because it's an essential nutrient. So everybody's constantly giving off small amounts of radiation. You live within 50 miles of a nuclear power plant for a year. That gives you 0.09 microsieverts. Sievert is an estimate of absorbed radiation. So eating one banana has more radiation than living within 50 miles of a nuclear power plant. Turns out nuclear power plants don't give off much radiation to the surroundings. They keep it all pretty well contained. In fact, where is living within 50 miles of a coal power plant actually has about 3 times as much annual radiation as living next to a nuclear power plant. Turns out coal power plants are actually way worse for everybody than nuclear power plants. Dental x-ray, 5 microsieverts. Background dose received by the average person over one normal day is 10 microsieverts. So basically you get an extra 50% of radiation exposure on the day that you get a dental x-ray. Which is also why the doctors and the dental hygienists leave the room, because if they were being exposed to that every day, 5 times a day, that would be a lot of radiation over time. But you getting one dental x-ray every 6 months is basically lost in the sick fix. So most radiation does the same stuff, causes genetic mutations, and the number one way that gets exposed or that you've noticed that is tumors.
So you often hear about the 3 Ds when you deal with radiation: dosage, duration, and distance from the source.
Yeah, and dose also factors in what type of radiation is it. So they actually have a combined unit. The sievert unit actually takes into account that an alpha particle is worse for you than a beta particle. So they wind up with all these combined units that are kind of hard to see how it all factors together, and it's all sort of kind of cobbled together over time. As they started doing more and more research on the effect of radiation on cells and different types of radiation. So all of these, you'll notice using a cell phone, 0 microsieverts. This used to be a thing that people talked about a lot. And actually, I guess with the 5G debacle, the radiation used by cell phones and cell towers is called non-ionizing radiation. It's low enough energy that it actually can't cause genetic mutations. So it is still technically radiation in that it's light, but it is actually lower in energy than the visible spectrum. So it actually can't cause any sort of radiation. Microwaves are the same way. Microwaves can't cause cancer because they only give off energy in the microwave region or in the radio wave region, which is not high enough energy for it to actually cause any sort of mutations. Yeah. You can burn your mouth. No, basically no. Like if you're using it as intended, if you took it apart and souped it up, you could make it so it gave off radiation that was ionizing radiation using some of the same pieces. But even that's going to be pretty hard to do. You're going to have to supply your own transformer, probably change out the filament. There's a lot of things you would have to do, but using it as directed, it really can't hurt you very much. Other than just straight, what microwaves do is they make water molecules move faster. So they heat things up if it has water in it. If you stuck your hand in there, then that would be a problem because you're basically going to boil the water in your hand and cause cell death in all of your cells that are getting exposed to that. But it's not, it's more just that you're heating it up than it is the microwave radiation. Leonore? Probably similar in a similar way that nuclear, because microwave ovens don't really use microwaves. They just use like a heat source. And so those toaster ovens is the term that I'm thinking of. Those toaster ovens basically can burn food, and burned food has free radicals in it. And free radicals, while they're not considered radiation, they can cause mutations in your cells. And so you have a better chance of getting cancer from a toaster oven than from a microwave. Nope. Not unless like really it just comes down to as long as you're not burning yourself, then they're pretty much safe. They're safer than using a barbecue grill. Vinny and then Zach.
There's like, they say like don't microwave some plastics, those plastics. So is that because it'll melt the plastic and then you'll ingest that, or just?
Partly. So certain plastics, when they get exposed to microwave radiation, they don't have the same type of bonds between atoms that we do. And so certain types of plastics, when they get above a certain, it's more about the temperature than it is the microwaves. When they get above a certain temperature, the plastic molecules start to break apart and produce free radicals. A free radical is just something that, like if you took two carbons, so let's say we're just looking at a really small molecule like ethane. But this applies to all carbon-carbon bonds, which is most of your body that's not water. If you shine the right wavelength of light on this, you can get this bond to split apart, and each one of those carbons takes one of the electrons. And so you would wind up making, it's not an ion, because if you actually count the number of electrons, it's a neutral carbon, but you get an unpaired electron as a result. An unpaired electron is called a free radical. So certain plastics, when you get above a certain temperature, they'll do that spontaneously. And if you ingest that, it basically goes and it finds another electron so that it can pair up, so that it can not be an unpaired electron. But if you have an odd number of electrons, you're always going to have an odd number of electrons, right? So it going around and grabbing other electrons causes this chain reaction. And if one of those happens to be a DNA molecule, you can wind up causing genetic mutations that way. So it's not the microwaves causing it. It's actually that the plastics split apart into free radicals. Some plastics actually will split apart into free radicals if you freeze them in the presence of water. So there's some types of like cheap single-use water bottles that are outlawed in Tahoe now. If you took those and froze them, you actually get measurable amounts of free radicals in the water that way. Zach and then Maddie.
Yeah,
So I believe that that has to do with the work function, which is basically if you heat certain metal, or if you expose certain metals to the right wavelength of radiation, you cause electrons to fly off by themselves. So it is kind of similar in that you get unpaired electrons, but it's actually just electrons flying off into space. And when those happen to hit other gas molecules that are in the microwave with it, it winds up arcing and causing sparks that way. So it's basically like creating little lightning strikes in there at the same time, but not all of the electrons get absorbed, and so it ruins the microwave because you wind up with those extra electrons flying off into the light source and causing problems that way. So there's a lot of reasons to not put metal in microwaves, and it mostly has to do with the metals that are, and it actually has to do with the shape of it too. I'm not suggesting anybody do this, but if you've ever microwaved a spoon on accident, spoons don't spark, but forks do. And it has to do with the shape of the tines on the fork, cause it to spark more than spoons. It's the rough corners. And it's probably to do with the type of metal that's coating it as well. There's less coating on the sharp parts than there is on the rounded spoons. Maddie. Okay. All right, just because this was the one thing that I wanted to make sure we already did, the equals MC squared calculation. Let's talk about this a little bit more. So that section up there, that's Chernobyl, spending 1 day or 1 hour. Where within the Chernobyl plant, where the Chernobyl plant was, there's still enough radioactive material that you would be absorbing more than you would get from almost anything else. But again, that's just 1 hour, and it does vary wildly depending on where you are, because Chernobyl power plant fragmented, right? So if you happen to be standing right on top of one of the fuel rods or something, or where one of the fuel rods was laying for a long time, you're going to get much higher exposure. And there's your normal yearly background dose. About 85% is from natural sources. And almost all the rest is from medical scans. And just because, yeah. Why didn't they turn blue? That's a good question. That's more of a medical question than a chemical question, and I don't know my anatomy and physiology well enough. But likely just because processes started breaking down, and whatever some process was producing something blue as it. What starts happening when you get a heavy dose of radiation poisoning is it basically knocks out certain systems in your body. The first system that gets knocked out is almost always your immune system. But then other systems start breaking down as well. So the actual mechanics depends a lot on where on your body you were exposed as well. Were you breathing in radioactive isotopes? That's going to affect different systems than if you got exposed to it through your skin, which is different than if you ingested it, if you ate it. Right? All of those are going to present differently. Yeah.
Area are gonna be radioactive.
10,000 years, I think, is the number I remember off the top of my head. And even then, it'll still be more radioactive than the surrounding area, but it'll be habitable. Without, wild genetic mutations, in about 10,000 years.
Still in the outer area, so like what, probably further away from that last one.
Yeah, and they do tourist trips where you can spend a couple hours in Chernobyl and go to visit the city, because it's wild if you've ever seen any pictures, because literally the sirens went off, everybody evacuated, and so it looks like everybody just disappeared. Like meals are still out on their tables, people are in the middle of making dinner. Actually, I think it was in the morning, so making breakfast, and they just left everything. Like It's really eerie, actually. It's, there's like tricycles on their side right in front of houses where people just picked up their kids and ran. So if it's definitely something it's really fascinating and very kind of creepy to look at. So if you're into that sort of thing, look up some pictures. So as I understand the story, the engineers at Chernobyl knew what was happening, but the military officials came in and said, we're running this test where we're going to shut down the safety procedure and see how well you deal with it. And the engineers like, no, we're not ready for that yet. We can't do that. We don't have the backups in place yet. And the military officials said, we're doing it anyway. So it was totally avoidable and man-made disaster. And so it was once that happened, happened very quickly. Sirens went off, people left, and within half an hour, everybody was out of the town because they knew it was serious. Because what happened is that I think they shut down the containment systems, the safety systems to test them, and then they couldn't bring them back up. And so basically they had zero containment after that point. And so there were a couple of people that were really critical in making sure that it didn't fully melt down and turn into a nuclear explosion at the cost of their own lives. They stayed behind to make sure that the cooling rods got inserted by hand. I think several of them actually had to climb into the nuclear reactor and put the cooling rods in by hand. And those are the ones that never even made it off the premises. I believe that there are still several bodies at the Chernobyl power plant because they're too radioactive to recover. So it was definitely, I've heard that the HBO series on Chernobyl, there's a mini series, there's like 6 episodes. I've heard that's very accurate. I haven't watched it yet. But if you're interested in seeing some of that, it's very, very telling. Vinny?
Do you think it's Chernobyl mostly nuclear right now?
Chernobyl and 3 Mile Island were the reason why nuclear power plants got such a bad rap in the 70s. 3 Mile Island caused some issues, but not nearly as bad as Chernobyl. We would definitely have more nuclear power plants if not for those, which is really too bad because even the Chernobyl power plant was built to such shoddy safety specifications that even in the 70s, it could not have been built in the US. Even in the 70s, with our 70s understanding of all these processes and ecology, we wouldn't have built Chernobyl like it was. Jason? It would not have been safer because it would have spread all that through the atmosphere. It would have it would have been like one of the largest volcanic explosions of all time. Everybody on Earth would have gotten a significant radiation dose. And everything downwind would have been uninhabitable. So at least it's contained. I'm gonna have to brush up on my knowledge of the A&P before I can answer that, but I believe so, yes. Like a really bad sunburn or like a burn eventually. Like it basically kills the tissue and your tissue starts falling off. Yeah.
Do you think the Chernobyl may have been an inspiration